A multitude of these units can be connected to the same power accumulating line via a freewheel clutch, transferring power from kilometers of ocean to a single point back on land. The design also has excellent storm survival characteristics. To reduce the force on the units, simply allow the power accumulating line to travel out from the generating station more quickly. If the units over travel, the surfaces are released to rotate, reducing their opposition to wave motion. Previous attempts have focused on converting mechanical energy into other types of energy, for example electrical or pressurized fluid, but they are still left with the expensive and impractical task of accumulating the energy and transferring it back to shore. Here is an example of the typical approach.
However, we have already failed to meet the 3.5 euro criterion. As you can see, offshore conditions imply some major obstacles. Most wave power projects unfortunately spend years optimizing their technology before they realize these unavoidable costs of full-scale conditions.
So to summarize, the main reason wave energy has not been successful is the cost of transferring energy back to shore, the cost of surviving storm conditions, and the cost of mooring points. So what is the most efficient way to transfer mechanical energy? A direct mechanical link. Existing cable technology can transfer energy cheaply and efficiently, for example in cable cars. The Genting Skyway in Malaysia stretches for over 3 kilometers. Its main drive has a power of 1.2 megawatts, and the energy is transferred over a mere 54mm cable. Our basic concept is to keep all electrical equipment safely on dry land. A high-strength cable stretches for several kilometers out into the ocean, gathering the wave energy. The energy is cheaply and efficiently transferred back to the shore, to the electrical generation station. But how do we transfer the energy from the waves to the cable? We need to apply a horizontal force, constantly pulling our cable away from the electrical generation station. The multiple panels can pivot freely on hinge connections to the frame. This minimizes resistance to wave motion in the direction of the pulley. The upper section of cable, being the slack section, is not connected to the frame and passes freely past. The lower section runs through the rollers and the clutch. When the panel is moving away from the pulley, the clutch engages and pulls the lower section of cable away from the pulley. When the panels are moving towards the pulley, the clutch disengages and the lower section passes freely through the clutch and roller. This operation is repeated with the wave motion. The circulating arrow shows the direction of wave motion. The unit oscillates back and forth along the power accumulating cable. The clutch intermittently grips the cable and applies force to it. The positioning line has stops which limit the distance of travel of the unit. The unit will tend to move towards the shore. When the unit reaches the stop, the flaps will pivot to minimize opposition to wave motion, allowing the positioning line to hold the unit in position. During extreme weather events, the unit may travel to the stop, which is away from the shore. When the unit reaches the stop, the flaps will be released to pivot to minimize opposition to wave motion, allowing the positioning line to hold the unit without putting excessive force on the positioning line. A multitude of these units can be connected to the same power accumulating line via a freewheel clutch, transferring power from kilometers of ocean to a single point back on land. The design also has excellent storm survival characteristics. To reduce the force on the units, simply allow the power accumulating line to travel out from the generating station more quickly. If the units over travel, the surfaces are released to rotate, reducing their opposition to wave motion. summary of the design advantages are: all electrical components are stored on dry land, minimal capital outlay costs, the method of transferring the power back to the shore is an inherent part of the design, minimal mooring costs, and excellent storm survival.